Welcome back everyone. Today we'll discuss a very good problem from 200 puzzling problem book, and it's kind of electrodynamics and SHM mixed in this problem. So we'll see that in the solution. Let's start. The problem states that a thin superconducting, obviously it will have zero resistance as it is a superconducting material. Ring is held above a vertical cylindrical magnetic rod as shown in the figure. The axis of symmetry of the ring is same to that of the rod. The cylindrically symmetrical magnetic field around the ring can be described approximately in terms of the vertical and radial components of the magnetic field vector as Bz equals to B naught into 1 minus alpha into Z, and Br, that is the radial component, is equals to B naught into beta times R, where B naught, alpha, beta all are constants and Z and R are the vertical and radial position coordinates respectively. Initially the ring has no current flowing in it. When released, it starts to move downwards with its axis still vertical. From the data below, determine how the ring moves subsequently and what current flows in the ring. And we have given the values of M, R naught, L, etc. An initial coordinate value I am marking here. It is given that initially it was Z at Z equals to 0 and R equals to 0. Right. So I'm writing phi, the flux through this superconducting ring, this ring, right? So it will be Bz times pi R naught square, because Bz is vertically upward in this direction, Bz, and this area is pi R naught square perpendicular to Bz. So we can directly write B dot A as Bz into pi R naught square, and Li term is due to self-inductance. Let's say I is the induced current in this ring, induced current in the ring. So that's the total flux, and I have substituted the Bz value, and obviously you can be very sure that Br will have no contribution towards the flux value, as the angle between Br and the plane of that ring is 0 degree, right? So there will be no flux contribution for the component Br. This is the value of Bz I have substituted as a function of Z. Now as it is a superconductor, we can claim that phi will be constant. Why? Because if phi is changing, I mean d phi dt is non-zero, then there will be infinite current induced. Or you can say it in this way, that the rate of change of flux, that is d phi dt or phi dot, should be equals to I times R. And as R is 0 for superconductors, phi dot should be 0. That implies that phi is equals to constant, right? So that's a very basic idea for superconductors, that phi remains constant with time as the resistance is 0. So this is the condition for superconductor. So we'll need some initial value or some known value of flux at any point of time, so that we can equate to that value of the flux at any time, for the flux at any time, right? So I'm just taking the initial value. Initially I was 0, that means the induced current was 0, and the Z coordinate was also 0 as it is given. So phi was basically putting Z equals to 0 and I equals to 0. We'll get phi at B naught pi R naught square, and this is the constant value, and this value will remain throughout the process, I mean the flux value. So I've just equated this initial value of magnetic flux with the flux value at any instant as a function of Z. From there we'll easily get the current value, I mean the induced current. So this is the expression for induced current. It is directly proportional to Z, so it will vary as the Z varies. So we'll use this relation later on. Let's move forward. Here I have shown the top view of that superconducting ring, and I have drawn the radial field lines, that is Br, and this one is Bz as you are viewing from above. So you will observe Bz's are coming out of the plane as I have shown. Now I am interested in finding out the force on that ring due to the magnetic fields, I mean for both the components. Now first I will tell that due to BZ component the force will be zero, magnetic force, due to symmetry. How? Because if you take a small element here, let's say ideal, so you do the ideal cross BZ, and one thing for sure that for all the points and all the current elements that we are taking on this ring, BZ value will remain same because it is a horizontal type ring, and Bz is just varying as a function of z. So z is constant for all the points, so Bz is also constant. In fact, Br is also constant by magnitude only. So we'll coming to the Br portion later on. First let's deal with Bz. If this is the ideal segment, so ideal cross Bz will be something like this. So this will be the df. So for all the current elements we will get some outward, radially outward df elements, and the diametrically opposite df elements for this one, this element will get cancelled out. So I'll finally claim that due to the symmetry, the force on that loop due to the Bz magnetic field part will be zero only, right? I guess it's very clear. So let me erase a few things. Okay, let it be there. Now I'm coming to Br part. So we are trying to find out the force on the loop or the ring due to Br part, I mean the radial component. So I've again taken an ideal element here, and this is the direction of Br, radially outward. So you do ideal cross Br. Here I have shown the directions. It will come inward to the plane of the paper, df, as ideal into Br. Now at every current element, if you take one here ideal, you will get the same value of df into the plane of the paper. You will get the same value of df. I'm not writing the value again. That will be ideal into Br, and Br is by magnitude constant on the circumference of the ring. Direction is different, obviously, radially outward at every point. So if we integrate, I mean we are trying to find out the total force. Integrating df, we will just integrate dl because I and Br are constant. So integration of dl will be total length of the circumference, that is 2 pi r naught. So this is the total downward force acting on the ring, and this is the I value. This is from equation number 1, as I have shown earlier here. I have substituted the value of I, 2 pi r naught, and this is the Br radial field value that is given in the question. So substituting all these values, we will get this one, that f is all these terms I am not reading out. So all these terms are constant. I have assumed a constant k just for a convenience of calculation, and there is a z also, so it's proportional to z, the downward force due to magnetic field. So now I am writing the second law of Newton's second law of motion for the ring, that is net force equals to mass times acceleration. So MAZ, because all the forces are in z direction, so we are just interested in z direction only. So MAZ will be equals to minus of mg, because mg is acting downward, and according to our assumption it's in negative z direction, and the magnetic force, that is F, we have calculated here, is also acting downward, that is negative z direction. So we have put a minus sign before mg and F both, and for F we have substituted k times z. So it's very clear that it's a kind of SHM equation. If you write this as a AZ, it will come out as minus g minus k upon m into z. So this is a constant force value, I mean the acceleration part due to a constant force, and this one is contributing to SHM, right? Because it is proportional to minus of z. AZ is proportional to minus of z. So this one will just contribute to a shift in equilibrium position, and from that reference, I mean from that equilibrium position, the ring will perform SHM, and for that SHM this will be the omega square value, I mean the angular frequency square, right? So it's almost analogous to the case, when you suspend a block from a spring under gravity, right? So there is always a constant force, gravity mg downward, but that will not contribute to the SHM, right? The SHM will be governed by the spring force only, that is kx value. So what gravity does, it just shifts the equilibrium position downward a bit, and from that equilibrium positions under the spring force, the block performs SHM. So it is kind of similar to that one. So we'll just claim from there that this will be the equilibrium position, because for to balance mg, the restoring force must be kz naught equals to mg. So z naught is mg upon k, and as it is in negative z direction, we are putting a minus sign, right? Whenever you are facing some problem, to understand, you just take the analogy that I have just said, that suspend a block from a spring in vertical direction under gravity. That's a very normal case, we frequently deal with that, and it is also analogous to that one. So now I am writing the SHM equation. This will look like something like this, because z naught is the equilibrium position and it will oscillate from z naught. So z minus z naught, this coordinate will be something like SHM. So I have assumed as a cos omega t. A is amplitude and omega is obviously the angular frequency, and omega is root under k upon m, we can conclude from here. And at time equals to 0, z was also 0, it was given. So using that equation, we will find out the a value. A is minus z naught. Now substituting all the values, we will get z as a function of time. This one. So that's our z. That's a major part we are done with, right? Now we are supposed to, this one was a part of question, right? Yeah, determine how the ring moves subsequently. So as it's a subjective question, our answer will be, it's a SHM motion, and its equation will be something like this. So that should be our answer for the first part. So let me highlight this one. And now we are trying to find out the current value. Then we'll again go back to the equation number 1, this one. Here all the terms were constant, but z was unknown, so we will just substitute the z value as a function of time. So we have just substituted the z value here, and subsequently we have got this. This is the Imax maximum current value, but I will not calculate. You can calculate the numerical value. All the numerical values are given of m, b naught, r naught, and everything. But that's the concept, I guess. I mean, it's a good problem, I guess, mixing the electrodynamics concepts and SHM. So yeah, that's all for today, and stay tuned. I will bring some more interesting problems. Thank you.